Measure the universe one way, and its expansion rate says one number. Measure it another way, and the answer completely changes. Both measurements are confirmed. Both are correct. Both are impossible simultaneously. The James Webb Telescope was built partly to solve this, but one of its recent discoveries has instead made the problem worse. That's right. The universe cannot agree on how fast it is expanding, and when you understand what that truly means, the implications are terrifying. Our best theory on this fundamental problem is now breaking apart from two directions at once. Tonight, we are going to trace every crack, follow every failed calculation, and arrive somewhere genuinely unsettling. Somewhere where modern physics just don't work. Stay until the end. Because the universe has been trying to tell us something for 15 years, and we are finally starting to hear it. If you're new here, welcome to the channel, get comfortable, and stay until the end. Because by the time this is over, the universe is not going to feel bigger. It is going to feel stranger, and that strangeness, confirmed, measured, and very much unresolved, is exactly where the most interesting science alive right now is happening. Now, let's get into it. Part 1. 2 answers, 1 universe. The universe is expanding. We know this. We have known it for nearly a century, ever since Edwin Hubble looked through a telescope in 1929 and noticed that galaxies were running away from us in every direction, like dots on a balloon being slowly inflated. That much is settled. What is not settled? What has become, in the last decade and a half, one of the most unsettling puzzles in the history of science, is how fast. You would think that would be a simple question. Measure the expansion, get a number, done. But here is where things get uncomfortable. When scientists measure the expansion rate of the universe using the early universe, the ancient light left over from the Big Bang, they get one answer. About 67 kilometers per second per megaparsec. And when scientists measure the same expansion rate using the nearby universe, stars and galaxies we can actually see and track, they get a completely different answer. About 73 kilometers per second per megaparsec. 2 measurements, 2 completely different numbers, and here is the part that should bother you deeply. Both of them are right, not approximately right, not right within some acceptable margin of error, right in the way that a bridge engineer needs to be right in the way that landing a spacecraft on Mars requires you to be right. These are careful, painstaking measurements made by different teams using different instruments, and they have been checked and rechecked and checked again. And they still disagree, by about 9%. In cosmology, 9% is not a rounding error. 9% is a screaming alarm. Think about what that actually means for a moment. Imagine you're baking a cake, and the recipe says it takes 45 minutes, but 2 different timers, both of which you have tested and confirmed are accurate, say the cake has been in the oven for 41 minutes and 49 minutes simultaneously. That is not a problem with the timers, that is a problem with time itself. And that is roughly the level of absurdity we're dealing with here. For years, astronomers tried to convince themselves this was a measurement error, an instrument not quite calibrated right, a technique with a subtle flaw, a dataset too small to be trusted. Scientists are patient people. They understand that precision takes time, so the community watched and waited and assumed that as the measurements improved, the 2 numbers would converge. They did not converge. They moved further apart. Then the James Webb Space Telescope launched. And if you were one of the scientists hoping that the most powerful space telescope ever built would finally put this argument to rest, you were right. Just not in the way you were hoping. Because what JWST found was not a correction. It was a confirmation. The nearby universe measurement, still 73, still stubbornly, infuriatingly 73. The last easy escape route, the hope that our local measurements were polluted by crowded star fields and optical illusions, quietly closed. And then, almost as if the universe wanted to make sure we were paying attention, the Atacama Cosmology Telescope, a completely different instrument, operating at the other end of Chile's high desert, measuring completely different physics, confirmed the early universe number. Still 67. Two completely different windows into the universe, separated by billions of years of cosmic history, each perfectly consistent with itself, each perfectly inconsistent with the other. So here is the question that should be keeping cosmologists up at night, and honestly should be keeping you up a little bit too. If both measurements are right, and they cannot both be right, then something in the foundation of our understanding of the universe is wrong. The question is not which measurement to trust. The question is what exactly is broken. And the answer to that question, as we're about to find out, might be more frightening than anyone expected. Part 2. The 15-year war over a single number. To understand why this crisis matters so much, you have to understand what the Hubble constant actually is. It is not just a speed. It is not just a number on a graph. It is the heartbeat of the cosmos. It tells you how fast space itself is stretching, not how fast galaxies are moving through space, but how fast the fabric of space is being pulled apart in every direction at once. It tells you the age of the universe. It tells you its size. It tells you its future. If your value of the Hubble constant is wrong, then everything built on top of it, every calculation about the size and age and fate of the universe, is also wrong. It is the kind of number where being off by 9% does not just mean your answer is slightly off. It means your entire picture of reality is distorted. The disagreement did not explode overnight. It crept in slowly, the way a crack in a dam appears long before the flood. In the early 2000s, measurements were still rough enough that the error bars on both sides overlapped, and physicists told themselves the discrepancy would sort itself out. By 2013, the European Space Agency's Planck satellite had measured the early universe with extraordinary precision and returned a confident answer of around 67. That same year, local measurements using Cepheid variable stars, pulsing stars that act like cosmic lighthouses, brightening and dimming on a schedule that reveals their true luminosity, were coming in closer to 73. The gap was about 5 kilometers per second per megaparsec, which sounds tiny until you realize that in cosmological terms, that gap represents a completely different universe. The tension, as scientists carefully called it, was about 3 sigma by the mid-2010s. In statistics, sigma is a way of expressing how unlikely something is to be random chance. 1 sigma is barely worth noticing. 2 sigma is interesting. 3 sigma means there is roughly a 1 in 1,000 chance the discrepancy is just noise. Physicists started writing papers, conferences dedicated entire sessions to the problem, and then gradually the tension crossed into 4 sigma territory. Then, by the early 2020s, it crossed into 5 sigma. 5 sigma is the threshold that physicists call a discovery. It means the probability that the discrepancy is a statistical fluke is roughly 1 in 3.5 million. When you cross 5 sigma in particle physics, you hold a press conference. You say you have found something real. And here was cosmology, staring at a 5 sigma discrepancy not in a new particle or a new signal, but in the most fundamental number in the entire field. A disagreement so statistically ironclad that by the rules physics uses to define reality, it counts as a confirmed discovery, except that what was being discovered was not a particle or a phenomenon. What was being discovered was a contradiction at the centre of everything. The 2 names you encounter most often in this debate are Adam Rees and Wendy Friedman. Rees, a Nobel laureate at Johns Hopkins, leads the team using Hubble Space Telescope data to measure Cepheid distances and arrives consistently at the higher 73 number. Friedman, at the University of Chicago, has spent decades on the same problem and has argued for a middle value, roughly 70, based on a different set of stellar distance indicators called the tip of the red giant branch. Their disagreement is not just about numbers, it is about how you build a case in science, about which rungs of the cosmic distance ladder you trust, about when you decide that your uncertainty estimates are correct and your competitors are slightly miscalibrated. It is the kind of debate where 2 brilliant people can look at the same universe, and reach irreconcilably different conclusions, while both following the rules of science perfectly. And that tension, not just the numerical tension, but the philosophical tension about the nature of evidence itself, is what makes the next chapter of this story so important. Because what happened when the James Webb Space Telescope turned its mirrors toward the same stars Rees and Friedman had spent their careers measuring changed the conversation in ways that neither camp had fully anticipated. Part 3, the moment JWST made it worse. The James Webb Space Telescope launched on December 25, 2021, a Christmas gift to humanity, depending on your tolerance for existential dread. It was, by every measure, a triumph of engineering. A 6.5-metre gold-coated mirror folded origami style into a rocket, unfolded in space 1.5 million kilometres from Earth, cooled to within a few degrees of absolute zero so that its infrared detectors could see through dust clouds and across billions of light years with clarity no previous telescope had achieved. It was the most expensive scientific instrument ever deployed, and one of the first things the cosmology community wanted to use it for was to settle the Hubble tension once and for all. The concern with previous Cepheid measurements was something called crowding error. When you look at a Cepheid variable star in a distant galaxy, through a ground-based or even Hubble-quality telescope, the star does not always appear alone. The image can blend neighbouring stars together into a single smeared dot of light. If you think you're measuring one bright Cepheid, and you're actually measuring a Cepheid plus several faint neighbours blended into the same pixel, you overestimate the brightness of the target, and that makes you underestimate its distance, which inflates your expansion rate. It is a subtle, technical error, exactly the kind of subtle, technical error that scientists had been hoping was inflating the local measurement and pushing it away from 67. JWST can resolve individual stars with far greater clarity than any previous telescope. Its infrared sensitivity cuts through dust. Its resolution separates stars that Hubble blurs together. So when Adam Rees and his team pointed JWST at the same host galaxies they had been measuring for years, they were essentially rerunning the experiment under conditions where crowding error, if it existed, would be exposed and corrected. The results came back in 2023. The Cepheid measurements held up, not approximately, precisely. The new, cleaner, higher resolution data confirmed the old results. The local expansion rate was still around 73. The crowding error hypothesis was dead. Think about what that moment means. For years, the critics of the high Hubble constant had a clean, reasonable argument. The local measurements are contaminated by a systematic error baked into the technique. It was a conservative position. It was scientifically responsible. And it was wrong. JWST had just eliminated the most technically credible way to explain the Hubble tension away, and in doing so had forced the community to confront something much more uncomfortable, that the data was clean and the problem was real. This is worth sitting with for a second because it is not the kind of result that gets a triumphant headline. It is the kind of result that makes physicists go quiet. Because when your best funded, most technologically advanced experiment confirms the thing you were hoping to disprove, you're no longer in the comfortable territory of suspicious data. You're in the territory of broken models. The universe is not behaving the way it should. And the James Webb Space Telescope, the instrument that was supposed to bring clarity, had instead brought certainty. Certainty that the problem is not the telescope. The problem is the theory. But just in case any lingering optimist thought the early universe side of this equation might still have some wiggle room, the Atacama Cosmology Telescope was about to close that door too. Part 4. ACT closes the other escape route. The Atacama Cosmology Telescope sits at an elevation of about 5,100 meters in the Chilean Atacama Desert, one of the driest places on Earth. At that altitude, the air is thin enough and dry enough to be nearly transparent to the microwave radiation left over from the Big Bang, the cosmic microwave background, or CMB, which is essentially a photograph of the universe when it was only 380,000 years old. If the JWST confirmation came from the near side of cosmology, from the universe as it exists today, and in the recent past, the ACT result came from the other end of time entirely. The European Space Agency's Planck satellite had already measured the CMB with extraordinary precision and returned the lower Hubble constant value of around 67. But the Planck measurement had critics, not because the data was bad, but because any measurement made by a single instrument comes with a built-in concern. What if there is a systematic error specific to that instrument that no one has detected? What if there is something about the way Planck measures temperature fluctuations in the CMB that subtly biases the result? That concern was not a fringe position. It was the kind of healthy scientific skepticism that good research requires. The Atacama Cosmology Telescope addressed that concern directly. Where Planck mostly measured the temperature anisotropies in the CMB, the tiny differences in temperature across the sky, ACT focused heavily on the polarization of that ancient light. Polarization and temperature are physically different aspects of the CMB signal. They are generated by different physics, they are measured with different detector technologies, and they are subject to different systematic errors. If Planck's result was an artifact of some technical quirk in temperature measurements, ACT's polarization-focused result would not necessarily reproduce it, but it did. The ACT analysis, published in 2025, returned a Hubble constant consistent with Planck, still 67, still irreconcilably different from the local 73. Two completely different instruments, two completely different measurement techniques rooted in different physics. Both pointed at the same ancient snapshot of the universe, and both reading the same number from it. The early universe, measured every way we know how to measure it, insists the expansion rate should be 67. The nearby universe, also measured every way we know how to measure it, insists it is 73. And the gap between them, 9%, 5 sigma, rock solid, is not going away. At this point, the scientific community was no longer dealing with a measurement problem. It was no longer about better instruments or larger data sets or more careful calibrations. Both ends of the measurement had been stress tested and confirmed. The problem was structural, and that meant the problem was theoretical, which is a much scarier place to be, because unlike instruments, you cannot just upgrade your theory with a new mirror or a better detector array. What could possibly explain two correct measurements of the same physical quantity that disagree by 9%? The answer, as it turns out, is that something in the universe changed between then and now. Something nobody predicted, something no current model accounts for, and something that, as we're about to see, may not be alone. Part 5. This is no longer a tension. There is a word that physicists use when two measurements disagree by enough to be interesting, but not quite enough to be disqualifying. That word is tension. It is a careful word, a diplomatic word. It says, we have noticed a discrepancy. We take it seriously, but we are not yet ready to declare that something fundamental is broken. Tension is the scientific equivalent of saying there is a slight concern about the structural integrity of the building while still renting out the office space. The Hubble tension has outgrown that word. 5 sigma is not tension. 5 sigma, a 1 in 3.5 million chance that the discrepancy is random, is a crisis. And the physics community has begun, slowly, and with the characteristic reluctance of people who have spent decades building the edifice in question, to start using that word instead. The model at risk here is called lambda CDM. Lambda stands for the cosmological constant, Einstein's term for the energy of empty space, which is what we now call dark energy. CDM stands for cold dark matter, the invisible mass that makes up most of the gravitating stuff in the universe. Lambda CDM is not just a model, it is the standard model of cosmology. It is the framework that explains the large-scale structure of the universe, the distribution of galaxies, the temperature fluctuations in the cosmic microwave background, the way galaxy clusters form and evolve. It has been tested against hundreds of independent datasets, and it has passed almost every test it has ever been given. It is, by the standards of science, an extraordinarily successful theory. But Lambda CDM makes a specific prediction. It says that if you measure the early universe precisely and extrapolate forward in time using the physics of the model, you should arrive at the expansion rate we see today, and it predicts that expansion rate to be around 67. The fact that the actual expansion rate today appears to be around 73 is not just a numerical disagreement, it is a direct falsification of a core prediction of the best cosmological model humanity has ever produced. Think about what it would mean for that model to be wrong. Every age estimate for the universe rests on it. Every prediction about how the universe will end rests on it. Every description of what dark energy is and how it behaves rests on it. If Lambda CDM is broken, then the scaffolding holding together our entire picture of cosmic history develops a crack that runs from the Big Bang to the far future, and the universe becomes, once again, a place we do not understand. And here is the part where this story gets darker still. Because while the physics community was still absorbing the confirmation from JWST and ACT, a completely different instrument, on a completely different mission, for a completely different reason, found something that suggested the problem was not just with how fast the universe is expanding, it also found something wrong with what is making it expand in the first place. Part 6. The 30 theories that didn't survive. When a major theory in physics develops a crack, the response from the scientific community is not panic, it is industriousness. Hundreds of theorists around the world pick up their pens or their keyboards because it is the 21st century and start proposing explanations. What could cause the universe to expand faster locally than it should based on early universe physics? The space of possible answers turns out to be enormous, and over the last 15 years, theoretical cosmologists have worked through that space with the methodical thoroughness of someone trying every key on an enormous key ring, one by one, in the dark. Some of the proposals were conservative. Maybe the dark energy that drives cosmic expansion is not perfectly constant. Maybe it varied slightly in the early universe, providing a brief burst of extra expansion just before the CMB was emitted. This idea is called early dark energy, and for a while it was one of the most popular candidates. It required relatively modest modifications to the standard model. It had testable consequences, and it could in principle explain why the locally measured expansion rate was higher than what the CMB predicts. The idea attracted serious attention and serious papers. Then the Atacama Cosmology Telescope tested it. By mapping the fine-scale structure of the CMB with high precision, ACT could constrain models of early dark energy tightly enough to check whether they matched the data. They did not. The ACT analysis systematically ruled out the versions of early dark energy that were proposed specifically to solve the Hubble tension. That was not the end of the genre. Theorists quickly moved to more elaborate versions, but the clean, elegant form of the solution was off the table. Exotic neutrinos were next on the list. Neutrinos are nearly massless particles that stream through the universe in unimaginable numbers. Trillions pass through your body every second without interacting with anything at all. In the standard model, there are 3 types of neutrinos, but theorists proposed a 4th type, a sterile neutrino that interacts only with gravity. If these particles exist in the right numbers with the right mass, they could alter the expansion history of the early universe in a way that shifts the predicted Hubble constant upward. The ACT dataset was sensitive enough to constrain the neutrino background with precision. Sterile neutrinos in the form needed to solve the Hubble tension were ruled out. New particles in general, light, fast-moving species that could inject extra energy into the early universe and drive it to expand slightly faster before the CMB formed, faced the same fate. ACT's polarization data placed tight constraints on the number of relativistic species in the early universe. Any new particle that contributed enough energy to meaningfully shift the Hubble constant would have left a detectable fingerprint. No such fingerprint was found. The exotic particle zoo was closed, one cage at a time. Modified expansion histories, where theorists played with the shape of the dark energy equation of state in the period before recombination, ran into the same wall. The CMB is extraordinarily sensitive to the expansion history of the universe. Anything that changes that history leaves a mark in the spacing of the acoustic peaks, in the polarization spectrum, in the damping tail. ACT checked all of these, and in paper after paper, the data came back clean, meaning no modification to the standard expansion history that was large enough to fix the Hubble tension was small enough to hide from the CMB. 30 proposed modifications. Not 30 vague hand-waving attempts, but 30 mathematically formulated, peer-reviewed theoretical frameworks, each one crafted by serious physicists to solve a serious problem. All of them either ruled out by the data or insufficient to close the gap. Every single key, tried in the dark, none of them opened the door. Which brings us back to the central question with exactly as much clarity as when we started, and that is to say, none at all. If the problem is not with the measurements, and the problem is not with any of the proposed theoretical fixes, then where exactly does that leave us? To answer that, we need to pull back for a moment and look at the escape route that still feels tempting to a lot of people, and explain why it is also a dead end. Part 7. The illusion of its just measurement error. There is a number that feels like a solution. It is approximately 70 kilometers per second per megaparsec. It sits almost exactly between the early universe value of 67 and the local value of 73, like a cosmological olive branch, and it has attracted the attention of researchers who believe the real answer lies in reassessing our distance measurements rather than rewriting fundamental physics. Wendy Friedman's work, using the tip of the red giant branch method instead of Cephids, has pointed in this direction. And for a while, the possibility that the middle ground was the right ground felt genuinely appealing. To understand why, you need to understand the cosmic distance ladder. Measuring distances in the universe is not like measuring the length of a table. You cannot run a tape measure to a galaxy 100 million light-years away. Instead, you build a ladder, a sequence of measurement techniques, each one calibrated against the rung below it and then used to reach the rung above. The first rung is parallax, the tiny apparent shift of a nearby star against the background sky as Earth moves around the Sun, from which you can calculate the star's distance using basic trigonometry. The second rung is Cepheid variable stars, calibrated using parallax measurements of nearby Cephids, and then used to measure distances to galaxies tens of millions of light-years away. The third rung is Type 1a supernovae, stellar explosions of consistent brightness, calibrated against Cepheids, and then used to reach galaxies hundreds of millions or even billions of light-years away. The Hubble constant lives at the top of this ladder. Every rung introduces uncertainty, and if there is a systematic error anywhere on the ladder, not a random error that averages out, but a consistent bias in one direction, that error propagates upward and distorts the final answer. The tip of the red giant branch method uses a different stellar phenomenon on a different rung of the ladder, which is why its results sometimes differ from the Cepheid-based approach. If the Cepheid measurements are slightly biased upward due to some unaccounted systematic, and the TRGB measurements are slightly biased downward due to a different unaccounted systematic, the two could be measuring the same underlying reality but reporting different numbers. The true answer, in this view, might be somewhere in the middle. It is a seductive argument, and it might even be partly right about the specific stellar physics involved. But here is the problem. Even if you remove the distance ladder entirely, the tension does not go away. Gravitational lensing offers a completely independent way to measure the Hubble constant that has nothing to do with Cepheids or red giants or supernovae. When light from a distant quasar passes around a massive foreground galaxy, the gravity of that galaxy bends the light along multiple paths, creating multiple images of the same quasar on the sky. Because each path is slightly different in length, the images do not flicker in synchrony. a variation in the quasar's brightness arrives at slightly different times, depending on which image you're watching. The time delay between images depends on the geometry of the universe, which depends on the Hubble constant. This technique, called time delay cosmography, uses completely different physics from any rung of the distance ladder. It does not care whether Cepheids are crowded or whether red giant branch calibrations are off by a few percent. The H0 lenses in Cosmograil's Wellspring collaboration, known as H0 Lycow, has used this technique on multiple lens systems and consistently found values above 70. Surface brightness fluctuations, a method that measures how smooth or grainy a galaxy looks based on its distance, also return values in the low 70s. A 2024 study of galaxy motions in the Coma cluster returned a value around 76. These methods are not climbing the same ladder, they are approaching the summit from entirely different sides of the mountain, and they are all arriving at roughly the same height, a height that is stubbornly, consistently above 67, so the middle value does not save us. It might describe the average of a range of measurements with different biases, but it does not explain why multiple completely independent physical methods using completely different rungs and completely different mountains keep arriving at values that are higher than what the early universe predicts. The escape route of measurement error, while still invoked in some circles, has been gradually bricked over by the accumulation of results from outside the distance ladder entirely. The universe is not giving us a measurement problem, it is giving us a physics problem, and to see just how deep that problem runs, we need to look at what happens when you approach the Hubble constant from multiple directions at once, because the view from all of them is pointing the same way. Part 8. The methods that shouldn't agree, but do. Here is what is most striking about the Hubble tension, once you look at it clearly. The problem is not that one technique gives 73 and everything else gives 67. The problem is that everything tied to the late universe, every method that looks at the cosmos as it exists today, or in the relatively recent past, gives a high value, and everything tied to the early universe, every method that reconstructs the cosmos as it was in its first few 100,000 years, gives a low value. The split is not between a few outlier measurements and a reliable consensus. It is a clean, systematic divide between two epochs of cosmic history. Gravitational lensing time delays measure the geometry of the universe right now, along specific lines of sight through the nearby cosmos. Surface brightness fluctuations measure distances to galaxies within a few 100 million light-years, using the statistical graininess of how their starlight distributes across a detector. Type 1, a supernovae measure expansion out to several billion light-years. The Coma cluster velocity result comes from the dynamics of galaxy motion in a nearby cluster. These are not variations on a theme, they are genuinely different physical phenomena, responding to different properties of the universe, measured with different instruments using different mathematics, and yet they cluster. They form a coherent group at 70 to 76, with the spread among them reflecting the genuine diversity of their methodologies, but all of them sitting above the early universe value by a consistent margin. If this were a measurement error, you would expect the errors to be random, some methods high, some low, scatter in both directions. What you see instead is a systematic pattern. The late universe says one thing, the early universe says another, and that is not a calibration problem. That is a story the universe is trying to tell us about its own history. One of the most compelling results in this category came from the Coma cluster analysis. The Coma cluster is a gravitationally bound collection of over 1,000 galaxies about 320 million light-years away, one of the densest and most well-studied galaxy clusters in the observable universe. A 2024 analysis using the peculiar velocities of galaxies within and around the cluster, the way their motions deviate from pure Hubble flow due to the gravitational pull of the cluster, returned a Hubble constant of approximately 76. The error bars on that measurement are still significant, so it should not be taken as a precise determination. But the direction of the result is entirely consistent with the broader pattern. The nearby universe, however you probe it, reads fast. The implication of all this is something that physicists have been dancing around for years, but are now starting to say more directly. The universe may have expanded differently in its early history than our standard model predicts. Something may have happened between the epoch of the CMB and the present day, something that accelerated the expansion rate beyond what lambda CDM expects. Not just dark energy, which we already knew was accelerating the expansion. Something extra, something the model does not contain, and whatever that something is, 30 proposed alternatives have already failed to identify it, which means we need to think bigger. And thinking bigger, it turns out, is exactly what the DESI collaboration was in the process of doing, except the results they found when they finished building the largest three-dimensional map of the universe ever created were not the kind of bigger thinking anyone was prepared for. Part 9. Why this is so dangerous scientifically. Before we get to DESI, it is worth stopping for a moment to appreciate what is actually at stake here, because the Hubble tension is not just an interesting puzzle about a number. It is a stress test of the entire theoretical framework that modern cosmology is built on, and the framework is starting to show cracks in places that were supposed to be load-bearing. Lambda CDM is an extraordinarily tightly constrained model. It has 6 free parameters, 6 numbers you feed it to describe the initial conditions and composition of the universe, and once you set those parameters using the CMB data, the model makes precise predictions about essentially every other large-scale observable in the cosmos. The mass function of galaxy clusters, the shape of the galaxy power spectrum, the baryon acoustic oscillation signal, the ratio of matter to dark matter. These predictions have been tested against independent datasets over and over again, and in almost every case, lambda CDM passes. It is, to use a word physicists rarely use without qualification, a successful theory. The core assumptions of lambda CDM are worth spelling out, because understanding what the Hubble tension threatens requires understanding what it assumes. First, the cosmological constant dark energy is exactly that, a constant. Not a varying field, not a dynamic entity, not something that was different in the past or will be different in the future. A fixed amount of energy per unit volume of empty space, everywhere, always. Second, the expansion history of the universe followed a specific trajectory, a period of inflation in the first fraction of a second, followed by a matter-dominated deceleration, followed by the relatively recent domination of dark energy driving accelerated expansion. This trajectory is precisely specified. Any deviation from it leaves a fingerprint in the CMB. And third, space on large scales is homogeneous and isotropic, the same in every direction and the same everywhere you look. No privileged directions, no special locations. The Hubble tension directly violates the consistency of the first and second assumptions. If the expansion rate today is genuinely higher than what early universe physics predicts, something changed during cosmic evolution in a way that lambda CDM does not account for. Either the expansion was briefly boosted by some additional physics in the period between the CMB and today, or the dark energy term is not as constant as assumed, or the expansion trajectory itself is different from what the model specifies. Any of these possibilities is, scientifically speaking, a major revision, not a tweak, not a footnote, a structural change to the most successful model in the history of cosmology. And here is the thing about structural changes. They tend not to come alone. When the foundations of a model shift, they shift across multiple predictions simultaneously. Other tensions start to appear. Other anomalies that were previously dismissed as statistical flukes start looking like a pattern. And indeed, when you look carefully at the CMB data and the large-scale structure data together, you find that the Hubble tension is not the only place where lambda CDM is under pressure. There is a tension in the clustering amplitude of matter, called sigma 8, where the model predicts slightly more clustering than we observe. There are mild anomalies in the CMB multipole spectrum that have resisted clean explanation. And now, most strikingly, there is what DESI found when it finished mapping 15 million galaxies. The model that was supposed to explain everything is cracking, and the cracks are not all in the same place. Part 10. The quiet shift in language. There is something important happening in the scientific literature right now that does not make headlines, but is, in its own way, a signal as clear as any telescope data. The language is changing. Papers that were describing the Hubble constant discrepancy as a tension 5 years ago are now describing it as a crisis. Cosmologists who were carefully hedging their conclusions with phrases like apparent discrepancy and subject to ongoing investigation are now using words like fundamental inconsistency and challenge to the standard model. This shift is not dramatic or sudden. It is the gradual change you would expect from a community that has been watching its most successful theory fail to explain a persistently confirmed observation for 15 years. In science, language matters. The word tension is a holding category. It means we see a problem, we're not sure whether it is systematic or real, we're gathering more data, we're being patient. The word crisis means something different. It means we have gathered enough data, we have eliminated enough systematic explanations, we're now in the territory where the theory itself has to be questioned. The transition from tension to crisis in the cosmological lexicon is the transition from suspicion to indictment. This shift has been accelerated by the convergence of evidence from multiple directions. It is one thing to have a single discrepant measurement from a single technique. It is another to have JWST eliminating the crowding error hypothesis, ACT confirming the low early universe value with independent physics, gravitational lensing and surface brightness fluctuations piling up on the high side, 30 alternative theories tested and ruled out. And then, just when the community might have hoped for a quiet moment to regroup, a new instrument with a new data set pointing at a completely separate problem that turned out not to be separate at all. Because that is what DESI did. The Dark Energy Spectroscopic Instrument was not designed to study the Hubble tension. It was designed to study dark energy, specifically to map the distribution of galaxies across cosmic time with enough precision to detect whether dark energy was behaving the way lambda CDM assumes, whether the cosmological constant was actually constant. And what it found has deepened this story in a direction that should make anyone who pays attention to the architecture of our current universe feel a profound sense of vertigo. The Hubble tension was always uncomfortable, but it was uncomfortable in the way that a locked door is uncomfortable. You know something is on the other side, but you do not know what. What DSI's results suggested was that maybe the door is not just locked. Maybe the entire wall is thinner than it looks, and to understand why, we need to talk about the force that is tearing the universe apart, what it is, what we assumed about it, and why the largest map of reality ever built is starting to make those assumptions look very, very fragile. Part 11. The largest map of reality ever built. There is a telescope in the mountains of Arizona, on a peak called Kitt Peak, that does not look like most people imagine a telescope should look. It has a 4-meter mirror, which is substantial but not remarkable by modern standards. What makes it extraordinary is not its size, but its eyes. The Dark Energy Spectroscopic Instrument, DESI, can observe approximately 5,000 galaxies simultaneously, splitting their light into spectra that reveal how fast each one is moving away from us, and, from that, how far away it is. In a single night of observing, DESI collects more galaxy spectra than some previous surveys gathered in a decade. Over its full survey, it is mapping the three-dimensional distribution of galaxies across 1/3 of the entire sky, reaching back 11 billion years into cosmic history. The point of building this map is to track a feature in the galaxy distribution called baryon acoustic oscillations. In the first few 100,000 years after the Big Bang, the universe was a plasma, a hot, dense soup of photons, electrons and protons in which pressure waves propagated like sound waves through the early cosmos. When the universe cooled enough for atoms to form, those pressure waves froze in place, leaving an imprint in the distribution of matter, a preferred spacing between galaxies, a scale at which galaxies cluster slightly more often than they would by chance. This preferred scale is about 500 million light-years in the current universe, It acts like a ruler, a standard length that you can observe at different epochs of cosmic history and use to measure how fast the universe was expanding at each epoch. Baryon acoustic oscillations are elegant because they are a feature of the early universe that we understand from first principles. The physics of pressure waves in a plasma is well understood. The scale of the BAO feature is calculable from the properties of the early universe that the CMB pins down with precision. So if you measure the BAO scale at multiple redshifts, multiple different cosmic epochs, you can trace the expansion history of the universe across time in a way that is largely independent of the messy astrophysics of individual stars or galaxies. It is the closest thing cosmology has to a clean, theory-independent measurement of how the universe is expanded. DESY's first data release, published in early 2024 after analysing data from the first year of a planned 5-year survey, covered about 6 million galaxies and quasars. The second data release, covering approximately 15 million objects, arrived in 2025. These numbers are not just impressive. They represent a dataset large enough to constrain the expansion history of the universe with a precision that was, until very recently, out of reach. And when the DESY team analysed that dataset, they found something in the expansion history that the standard model does not predict. Something that connects, in a deeply unsettling way, to the Hubble tension. Part 12. Dark energy was supposed to be simple. In 1998, 2 independent teams of astronomers were using Type 1a supernovae to measure the expansion rate of the universe. The goal was to measure how much the expansion was slowing down due to gravity, a number called the deceleration parameter. Every cosmologist in the room expected the expansion to be decelerating. Matter attracts matter. The Big Bang had sent the universe flying outward in all directions, and gravity should have been gradually slowing that expansion, the way a ball thrown upward gradually loses speed before falling back down. Both teams found the opposite. The expansion was not slowing down, it was speeding up. Galaxies were accelerating away from each other. Something was pushing space apart with an energy that not only resisted gravity but overpowered it at cosmic scales. This discovery, which earned its discoverers the Nobel Prize in Physics in 2011, introduced what became the central mystery of modern cosmology: dark energy. Some form of energy, invisible and spread uniformly through all of space, was driving the universe to expand faster and faster. Einstein had actually predicted something like this. When he first wrote down the equations of general relativity in 1915, they described a dynamic universe, one that would either expand or contract. Einstein was disturbed by this, because at the time most scientists believed the universe was static, eternal, and unchanging. So he added a term to his equations, the cosmological constant, denoted by the Greek letter lambda, that represented a uniform energy density of empty space, a kind of built-in repulsion that could balance gravity and keep the universe static. When Hubble showed in 1929 that the universe was in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. Then the 1998 supernova discovery brought it roaring back. In lambda CDM, dark energy is that cosmological constant. It is the simplest possible form of dark energy, a fixed value, unchanging in space and time, identical everywhere in the universe throughout all of cosmic history. Its equation of state, the ratio of its pressure to its energy density, has the value -1. That -1 is important. It means dark energy does not dilute as space expands. It does not cluster. It does not evolve. It is the same today as it was 1 billion years ago, and the same as it will be 1 billion years from now. It is the most boring possible form of dark energy, and in physics, boring is usually good. Simple, elegant, constant. That is the lambda of lambda CDM. If that constant is actually constant, then the fate of the universe is sealed. The expansion will continue to accelerate forever. galaxies beyond our local group will eventually recede faster than light, becoming permanently unreachable and then invisible. The universe will end not with a crunch, but with an extraordinarily slow, cold fade. A heat death trillions of years from now where entropy has reached its maximum, stars have burned out, black holes have evaporated, and nothing remains but diffuse cooling radiation in an ever-expanding void. It is a bleak fate, but it is a definite one, and it rests entirely on that negative one. DESI did not find negative one, and that is where the second crack in our understanding of the universe appeared. Part 13, DESI's disturbing signal. When the DESI team analysed their baryon acoustic oscillation measurements across multiple redshift bins, spanning a range of cosmic history from about 11 billion years ago to the relatively recent past, they were testing whether the expansion history of the universe matched what a constant dark energy term would predict. In lambda CDM, dark energy with an equation of state of -1 produces a specific expansion trajectory. The universe accelerates at a specific rate. The BAO scale at each epoch shifts in a specific calculable way. If lambda CDM is right, all of DESI's data points should line up along that trajectory. They did not line up perfectly. The DESI data suggested that the dark energy contribution to the expansion was not constant. Instead, it appeared to have been stronger in the past and weaker in the present, or more precisely, that the equation of state parameter denoted W was evolving over time. The analysis used a two-parameter model for evolving dark energy, where W0 describes the current value and WA describes how fast it is changing. A cosmological constant gives W0 equals -1 and WA equals 0. What DESI found across multiple datasets and multiple analysis choices was a preference for a value of WA that was negative, meaning dark energy appeared to have weakened as the universe aged. The statistical significance of this signal ranged from about 2.8 sigma in the first data release to as high as 4.2 sigma when the DESI BAO data was combined with supernova surveys and CMB data. 4 sigma is not 5 sigma. It is not yet at the official threshold for a discovery in the particle physics sense. But it is substantial. It is the kind of signal that in most branches of physics would be considered highly suggestive of a real effect. And crucially, it appeared consistently across different analysis methods, different combinations of external data sets, and different theoretical parameterizations of dark energy evolution. What would it mean for dark energy to be weakening? The straightforward interpretation is that the force driving cosmic acceleration is not a fixed property of space itself, but something more dynamic, a field, perhaps, that has energy and can evolve over time. In the far future, if this trend continued, dark energy could weaken further. The acceleration of the universe's expansion could slow down. Eventually, in this scenario, the acceleration could stop entirely. The universe could begin to decelerate. And if the dark energy field eventually reverses, if it transitions from repulsive to attractive, the expansion of the universe could halt and reverse. The cosmos could begin to contract. What began with a big bang could end with a big crunch, or perhaps a big bounce into a new cycle of existence. These are not certainties implied by DESI's data. They are possibilities opened up by it. And the difference between certainty and possibility, in this context, is the difference between a universe with a known fate and a universe that has surprised us again. But here is the part of the DESI result that connects directly back to the Hubble tension, because it turns out these two anomalies are not independent problems. They are, in a sense, the same problem wearing two different faces. Part 14, the worst part, it makes everything worse. When theorists noticed the DESI signal for evolving dark energy, one of the first things they did was ask how that evolution would affect other cosmological measurements. If dark energy is not constant but instead varies over cosmic time, then the expansion history of the universe is different from what lambda CDM assumes. Different expansion history means different predictions for everything built on top of that history, including the Hubble constant. The result of that analysis was deeply unwelcome. When you allow dark energy to evolve in the way DSI's data suggests, weaker today than in the past, and you recalculate the cosmological model with that evolution included, the Hubble tension does not improve. In most parameterizations, it gets worse. The reason is subtle but important. Evolving dark energy changes the calibration of the sound horizon in the early universe, which is the fundamental scale that the CMB-based Hubble constant measurement relies on. If that scale shifts, the inferred Hubble constant from the early universe shifts too, and the direction of the shift tends to push the early universe value further from the local value, not closer to it. So DSI did not solve the Hubble tension. It made it more complicated. It introduced a second anomaly that, when incorporated into the theoretical framework, tends to exacerbate the first. The universe handed us a new puzzle, and the new puzzle made the old puzzle harder. This is the kind of scientific situation that is technically described as a mess, though the papers use somewhat more careful language. Think about what physics now has to explain simultaneously. The local universe is expanding at about 73 kilometers per second per megaparsec. The early universe predicts 67. The difference is 5 sigma and has survived every instrument upgrade and independent check we have subjected it to. On top of that, the force driving the expansion may not be the cosmological constant at all, but something that is evolving over time, weakening as the universe ages, or possibly varying in a more complicated way. And when you try to build a single theoretical framework that explains both of these things simultaneously, the models that accommodate the DESI dark energy signal tend to make the Hubble tension worse rather than better, while the models that alleviate the Hubble tension tend to conflict with what DSI is finding about dark energy. There is a word for what happens when the anomalies in a physical theory stop being independent and start interacting with each other in ways that compound the problem. Cosmologists might call it a coherent pattern of failure. A more colloquial way to say it is that we did not just find another crack in the wall. We found out that the two cracks are connected. And connected cracks, as any structural engineer will tell you, are considerably more alarming than isolated ones. Part 15. The convergence problem. Step back from the technical details for a moment and look at the shape of what has happened in the last 3 years of cosmology. Not the individual data points, not the error bars, not the sigma values, just the shape. Because when you zoom out far enough to see the whole picture at once, what you find is not a collection of isolated puzzles waiting to be solved one by one. What you find is a pattern, and the pattern is the kind that, in the history of physics, has only ever meant one thing. We have the James Webb Space Telescope confirming the local Hubble constant with unprecedented precision. The concern for years had been that nearby Cepheid measurements were contaminated, that the pulsing stars used as cosmic distance markers were being blended together in crowded star fields, their brightness artificially inflated, their distances underestimated, their implied expansion rate pushed too high. JWST's resolution was supposed to expose that error. Instead, it eliminated the hypothesis entirely. The stars were clean, the distances were accurate. The local expansion rate came back at 73 kilometers per second per megaparsec, as reliable and well measured as any number in observational cosmology has ever been. That door closed quietly in 2023 and it has not reopened. We have the Atacama Cosmology Telescope confirming the early universe Hubble constant using completely independent physics. Where JWST looked at individual stars in nearby galaxies, objects you could, in principle, point a sufficiently powerful amateur telescope toward and see as faint smudges of light. ACT looked at the polarization of microwave radiation left over from an epoch 13 billion years ago, when the universe was a plasma so hot and dense that no atom had yet formed. No star existed. No galaxy was even a theoretical possibility. Different instrument, different wavelength, different physical phenomenon, different team of scientists on a different continent using different analysis software. Same answer as Planck, 67, equally clean, equally reliable. The early universe, measured 2 independent ways, insists on 67, with the same confidence that the nearby universe insists on 73. We have 30 theoretical modifications, not 30 vague suggestions, but 30 mathematically formulated, peer-reviewed proposed solutions, tested against the ACT dataset and found insufficient. Early dark energy, in its cleanest form, ruled out. Exotic neutrino species, ruled out. New relativistic particles, ruled out. Modified expansion histories, ruled out. Each one tried seriously, each one failing its first real confrontation with high-precision data. The theoretical escape routes have not just been explored, they have been systematically closed one by one, with the methodical patience of people who understood exactly what it would mean if none of them worked. None of them worked. And now we have the Dark Energy Spectroscopic Instrument, using a completely different technique from any of the above, baryon acoustic oscillations, the frozen imprint of ancient pressure waves, measured across 15 million galaxies spanning 11 billion years of cosmic history, finding independent evidence that the dark energy content of the universe is not behaving the way the standard model assumes, not varying wildly, not collapsing dramatically, just quietly, persistently, stubbornly failing to match the flat, constant value that lambda CDM requires. The equation of state parameter that should sit at -1 appears to be doing something else, something that changes over time, something that, in at least some analyses, suggests the force driving cosmic acceleration was stronger in the past and is weakening in the present. Now pause and appreciate what these 4 results actually represent in terms of their physical origins, because this is the part that makes the pattern so difficult to dismiss. The JWST result comes from measuring individual pulsing stars, Cepheid variables, objects that brighten and dim on a precise schedule that reveals their true luminosity, located in galaxies tens of millions of light-years away. The physics involved is stellar astrophysics, nuclear burning in evolved stars, pressure and gravity oscillating in a careful balance, light curves measured in optical and infrared wavelengths over weeks and months of observation. This is about as local and concrete as cosmological measurement gets. The ACT result comes from the polarization of microwave photons that have been travelling through space since the universe was 380,000 years old. The physics involved is plasma physics and radiative transfer in the primordial fireball, imprinted on the sky as a faint pattern of orientation in ancient light, measured at millimetre wavelengths by detectors cooled to within a fraction of a degree of absolute zero on a mountaintop in Chile. This is about as distant and abstract as cosmological measurement gets. The DSI result comes from counting galaxies, millions upon millions of them, each one a gravitationally bound collection of hundreds of billions of stars, each one's distance determined by the stretching of its light across cosmic time, and looking for the subtle, statistical preference in their 3-dimensional clustering that reflects the frozen scale of those ancient pressure waves. The physics involved is large-scale structure formation, gravitational dynamics, and the statistical analysis of a dataset so large it required purpose-built supercomputing pipelines to process. These could not be more different in their physical basis. They share essentially nothing in terms of technique, instrument, wavelength, epoch, or underlying astrophysics, and they are all pointing in the same direction. Something is wrong with our model. Not wrong in the way that a measurement might be wrong, with a sign error or a miscalibrated detector or a miscounted background source. Wrong in the way that a theory is wrong when the universe systematically refuses to conform to its predictions no matter how many completely different ways you look at it. That is a different category of wrong. That is the kind of wrong that does not get fixed with a better telescope or a larger data set. That is the kind of wrong that requires a new idea. In the history of physics, this is a recognizable pattern. It has a shape, and scientists who know their history can feel that shape when they are inside it, even before the resolution arrives. The pattern is this: multiple anomalies, each individually explainable in isolation, each individually survivable by the existing theory, accumulate from independent directions until the weight of their convergence makes the existing framework no longer tenable. Not wrong in every prediction, the framework may still work beautifully for most purposes, the way Newtonian mechanics still works beautifully for calculating the trajectory of a thrown ball. But missing something fundamental, something whose absence distorts a specific class of predictions in a specific consistent way, something that, once identified and incorporated, will require a reorientation of how we think about the system at the most basic level. This is precisely the pattern that preceded quantum mechanics. Classical physics in the late 19th century was extraordinarily successful. It explained the motion of planets, the behaviour of electricity and magnetism, the propagation of waves, and then it kept failing, in two specific and stubborn ways, to predict the behaviour of light and matter at the atomic scale, the blackbody radiation spectrum, the photoelectric effect. No classical fix worked. Every proposed modification preserved the failure. The problem was not with the experiments. The problem was that classical physics was missing the concept of quantization, the idea that energy comes in discrete packets, which was so foreign to the conceptual framework of the time that it took nearly 3 decades and the combined efforts of Planck, Einstein, Bohr, Heisenberg, Schrödinger and others to fully work out its implications. When they did, the result was not a correction to classical physics. It was a new branch of science that changed our understanding of matter, energy and reality at the most fundamental level. This is also the pattern that preceded general relativity. Newtonian mechanics was the gold standard of physical theory for over 200 years. It predicted the motions of the planets with extraordinary accuracy, with one exception, a tiny, persistent 43 arc second per century discrepancy in the precession of Mercury's perihelion. Astronomers proposed an undiscovered inner planet. They modified the inverse square law. They calculated atmospheric and tidal effects. Nothing worked. The discrepancy required Einstein to reconceptualize gravity itself, not as a force acting between masses across empty space, but as the curvature of space-time caused by the presence of mass. A conceptual revolution, triggered by 43 arc-seconds per century, that reshaped our understanding of space, time, and the universe. The Hubble tension is bigger than 43 arc-seconds per century. It is a 9% discrepancy confirmed at 5 sigma from multiple independent directions. The DESI dark energy signal compounds it. The JWST early galaxy anomalies add pressure from another direction entirely. Multiple anomalies, independent methods, all converging on a common message. The current framework is insufficient, not useless, but missing something fundamental, something that, once found, will require a reorientation of how we think about the universe at the most basic level. The question that physics is now genuinely, unavoidably facing is what that something is. And to begin answering it, we need to venture into territory where the data runs out and the careful, peer-reviewed certainty gives way to something rawer and stranger, the territory of speculation, which in cosmology right now is not the comfortable realm of distant possibility it once was. The speculations on the table today are not gentle, they are not minor, and some of the physicists entertaining them most seriously are not entirely sure they are ready for the answers. Part 16. If dark energy evolves, everything changes. Let us take the DESI signal seriously for a moment, not as a provisional curiosity, not as an interesting anomaly worth monitoring, not as the kind of result that gets filed under promising but premature. Let us assume it is real. Let us assume that what the largest three-dimensional map of the cosmos ever constructed is telling us is actually true, that dark energy is not a cosmological constant, not a fixed, eternal property of empty space, not the unchanging lambda that Einstein reluctantly introduced and modern cosmology gratefully inherited. Let us assume it is something dynamic, something that has been evolving, something that has been weakening as the universe ages, like a battery that was fully charged at the beginning and has been slowly, imperceptibly draining ever since. If that is true, if the DESI signal holds up under the scrutiny of future data and independent replication, then the implications unspool in directions that range from the scientifically revolutionary to the genuinely, quietly terrifying. The first and most immediate implication is one that tends to get lost in the technical discussion, but deserves to be stated plainly. Our prediction of the universe's future is wrong, not updated, not refined. Wrong in the structural sense, the way a weather forecast is wrong when it predicts sunshine and you wake up to a storm, except the forecast we're talking about is not for tomorrow. It is for the next 100 billion years. The standard lambda CDM picture of the universe's fate is one of the most confident long-range predictions in all of science. Eternal acceleration, the expansion of space continuing indefinitely, driven by the constant pressure of dark energy against the pull of gravity. Galaxies beyond our local group receding faster and faster until they cross the cosmic horizon and vanish permanently from our observable universe. Stars burning out over trillions of years. Black holes evaporating over timescales so long they make the current age of the universe look like the first fraction of a second. And then, eventually, a final state of maximum entropy. The heat death. A universe so expanded and so cold and so uniform that nothing further can ever happen in it. No gradients, no energy flows, no complexity. Just an infinite, dark, cooling expanse of diffuse radiation, expanding forever into a future without events. That picture was built on one assumption above all others, that dark energy is constant, that the lambda term in Einstein's equations is a true constant, the same value at every point in space, at every moment in time, from the Big Bang to the infinitely distant future. If that assumption is wrong, if dark energy is not a constant but a field, not a fixed property of the vacuum but a dynamic quantity that evolves over cosmic time, then the fate of the universe is not sealed. It is contingent. It depends on what dark energy does next, and we now have evidence, imperfect and preliminary but real, that what it does next is not necessarily what our model assumed. The forecast is wrong. We just do not yet know by how much or in which direction. To understand the range of possibilities that open up once you allow dark energy to evolve, it helps to spend some time with the theoretical framework that has been developed over the last 3 decades to describe exactly this scenario. The physicist Paul Steinhardt at Princeton University is one of the architects of inflationary cosmology, one of the people who helped develop the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, smoothing out its initial irregularities and seeding the structures that would eventually become galaxies and galaxy clusters. He is not a marginal figure. He is one of the foundational theorists of modern cosmology. And for much of his career, he has been deeply skeptical of the cosmological constant as an explanation for dark energy, not because he doubts the observations, but because he finds the cosmological constant theoretically unsatisfying in ways that he believes point towards something more interesting underneath. The framework Steinhardt and his collaborators developed is called quintessence. The name comes from the ancient Greek concept of a fifth element, the substance of the heavens, beyond earth, water, fire, and air, and it describes a class of models where dark energy is not a property of the vacuum, but a dynamical field that permeates all of space and evolves over time, like the Higgs field, which gives elementary particles their mass by filling all of space with a non-zero value, or like the inflaton field that is hypothesized to have driven the exponential expansion of the early universe. A quintessence field has energy stored in it that can change as the field evolves. The field rolls, slowly, over cosmic timescales, down a potential energy landscape, the way a ball rolls down a hill, and as it rolls, the energy associated with it changes, sometimes slowly, sometimes quickly, depending on the shape of the potential. In the gentler versions of quintessence, the field rolls so slowly that its effective dark energy density barely changes over the 14 billion years the universe has existed so far. It looks to current observations almost exactly like a cosmological constant, but eventually, in the far future perhaps, the field reaches a steeper part of the potential, and begins to roll faster. The dark energy density drops. The acceleration of cosmic expansion slows. The universe's expansion rate begins to decrease, not immediately, not catastrophically, but inexorably, over timescales of billions or tens of billions of years. The eternal acceleration of the standard model gives way to a deceleration, a gradual transition from a universe driven apart by dark energy to one where gravity, never defeated, begins to reassert itself on the larger scales. In the more dramatic versions, the quintessence field does not merely weaken, it changes sign. It transitions from a field with positive potential energy, which acts repulsively, pushing space apart, to one with negative potential energy, which acts attractively, pulling space together. When that happens, the consequences cascade. The accelerating expansion of the universe not only slows but stops. The cosmic horizon, which had been receding as distant galaxies accelerated away, begins to contract. Galaxies that had been permanently beyond reach begin, almost imperceptibly at first and then with increasing speed, to approach. The large-scale structure of the universe, the web of filaments and voids and galaxy clusters that formed over billions of years of gravitational growth, begins to reverse its expansion. Everything that the Big Bang sent flying outward begins, eventually, to fall back. The universe contracts, space shrinks, density rises, temperature climbs, and the cosmos retraces, in reverse and at accelerating speed, the journey it took from the Big Bang to the present day, compressing everything that existed across 14 billion years of expansion back down into a state of unimaginable density. Perhaps a singularity, perhaps something that physics as currently understood cannot describe, or perhaps, and this is the possibility that Steinhardt and others have explored with particular care, a bounce. A transition point at which the contracting universe does not collapse into a singularity, but instead undergoes a new period of rapid expansion, a new Big Bang, a new cycle, a cosmos that does not have a beginning and an end, but a rhythm, expanding, contracting, bouncing, expanding again, cycling through states of low and high density across timescales that make the current age of the universe seem like a single heartbeat. These are not the musings of fringe theorists working outside the mainstream. Steinhardt's quintessence models are mathematically rigorous, published in the highest tier journals, and taken seriously by the cosmological community, even by those who ultimately prefer the cosmological constant interpretation. The cyclic universe models he developed with Neil Turok represent one of the most carefully worked out alternatives to the standard inflationary picture of cosmic origins, and the DESI data, if it holds up, is consistent with the early stages of precisely the kind of dark energy evolution these models predict. The weakening equation of state that DESI's baryon acoustic oscillation measurements suggest is not inconsistent with a quintessence field that has been slowly rolling for billions of years and is beginning to enter a steeper region of its potential. It is, in other words, the kind of signal you might expect to see first, subtle, statistical, hovering just above the threshold of detection if the universe's dark energy were genuinely evolving in the way these models describe. That possibility, if confirmed by future surveys with greater statistical power, would rank among the most consequential scientific discoveries in human history. The qualification about daily life is worth making. These timescales are incomprehensibly remote, measured in billions and tens of billions of years, and no reversal of cosmic expansion would affect our galaxy, our solar system, or any conceivable descendant of human civilization for an almost unimaginably long time. In any practical sense, the difference between eternal acceleration and eventual contraction is irrelevant to anyone alive today, or likely to be alive for billions of years to come. But science is not only about the practical, it is about the true. And the truth of whether the universe expands forever or eventually turns around, whether the cosmos has a final state or a rhythm, whether the Big Bang was a beginning or a transition, is one of the deepest questions physics has ever asked. A universe whose dark energy evolves is a universe that is not as simple, not as settled, and not as fully understood as the standard model implied. It is a universe that is still in the middle of its story, a universe that has more structure to its future than we assumed, and a universe that may, in its very dynamics, be carrying the memory of a past that predates everything we currently call the beginning. Part 17. The radical fixes now on the table. When conservative solutions fail, and we have established methodically and without much comfort that 30 of them have, physicists start reaching for the tools they normally keep locked in a cabinet labelled for emergencies only. Not because they are reckless, not because they have abandoned the careful, evidence-driven discipline that makes physics trustworthy, but because the evidence itself has driven them there. When the data eliminates every modest fix and the anomaly refuses to shrink, the responsible scientific position is not to keep proposing smaller and smaller adjustments to a framework that has already survived 30 challenges and failed all of them. The responsible position is to start asking whether the framework itself needs to be rebuilt. That is where cosmology is right now, and the proposals on the table reflect exactly how serious that situation has become. The first thing to understand about these proposals is what separates them from everything that came before. The 30 modifications that failed were, by and large, additions to lambda CDM. They proposed new particles, new energy components, new behaviours in specific epochs of cosmic history, but they left the basic architecture of the model intact. Dark matter still gravitated. Dark energy was still essentially a property of the vacuum. General relativity still governed the expansion. The modifications were like adding rooms to a house. You are changing the floor plan, but the foundation, the load-bearing walls, the structural skeleton, those remain. What the current generation of proposals is contemplating is something more fundamental. They are not adding rooms, they are questioning whether the foundation is the right material. One of the most actively developed directions involves a direct interaction between dark matter and dark energy, a coupling between the two dominant components of the universe that lambda CDM explicitly assumes does not exist. In the standard model, dark matter and dark energy are parallel tracks. Dark matter gravitates, pulling matter together, seeding the formation of galaxies and galaxy clusters. Dark energy repels, pushing space apart, driving the accelerating expansion. They coexist in the same universe, they both shape its evolution, but they do not exchange energy or momentum. They do not talk to each other. This assumption of non-interaction is not based on any deep theoretical principle. It is essentially a simplifying assumption, the kind of assumption you make when building a model, because it keeps the mathematics tractable, and because you have no evidence yet that it is wrong. The question is whether it is actually right. Theorists have proposed a family of models, collectively called interacting dark sector models, where dark matter and dark energy are coupled, where energy flows between them over cosmic time in a way that alters the expansion history of the universe. The physics of how this coupling works varies considerably between different implementations. In some models, dark energy decays into dark matter over time, gradually transferring its energy into the gravitating sector. In others, dark matter converts into dark energy, changing the balance of the two components as the universe ages. In still others, the interaction is mediated by a new force that operates only between dark sector particles, invisible to ordinary matter and to any detector we currently have. The common thread is that the effective dark energy density, the amount of dark energy available to drive cosmic expansion at any given epoch, changes over time not because the dark energy field itself is dynamic, but because energy is flowing in or out of the dark sector through this interaction. Some versions of interacting dark sector models can simultaneously accommodate the DESI signal and reduce the Hubble tension. When the coupling is tuned appropriately, the expansion history shifts in a way that brings the early universe prediction of the Hubble constant closer to the locally measured value, while also producing a dark energy equation of state that varies over time in a manner consistent with what DESI found. That is an appealing feature. A single new ingredient that addresses two separate anomalies at once is exactly the kind of theoretical economy physicists find attractive. The problem is the other side of that coin. These models introduce new free parameters, numbers describing the strength and nature of the dark sector coupling, that current data cannot tightly constrain. Different choices of those parameters produce meaningfully different predictions. It is not a single theory that can be tested and confirmed or ruled out. It is a family of theories, a large space of possibilities, and navigating that space requires data that does not yet exist. Future surveys, the Vera Rubin Observatory's legacy survey of space and time, the Euclid satellite's galaxy weak lensing maps, the next generation of CMB experiments will constrain the dark sector coupling more tightly. But for now, interacting dark sector models represent a direction rather than a destination. Modified gravity is a direction that carries even more radical implications, because it does not merely add a new component to the universe, it revises the law that governs how all components interact. General relativity is one of the most precisely tested theories in the history of science. In the solar system, its predictions for the bending of light, the gravitational redshift of clocks, the precession of planetary orbits, and the behaviour of GPS satellites have been confirmed to extraordinary precision. In the strong field regime, the gravitational wave signals detected by LIGO and Virgo from merging black holes and neutron stars match general relativity's predictions, with a fidelity that leaves essentially no room for deviation. These tests are impressive, but they all operate on scales ranging from meters to roughly the size of a solar system. The cosmological regime, distances of hundreds of millions to billions of light years, timescales comparable to the age of the universe, is a domain where general relativity has been far less rigorously tested, for the simple reason that designing controlled experiments at cosmological scales is not something any laboratory can do. Scalar tensor theories represent the most developed class of modified gravity proposals for cosmology. In these theories, gravity is not described purely by the curvature of space-time, as in general relativity, but by a combination of space-time curvature and an additional scalar field that permeates the universe and modifies the effective strength of gravity on large scales. The scalar field can be nearly invisible on solar system scales, screened by local density in a way that explains why solar system tests pass, while producing measurable deviations from general relativity on cosmological scales where the screening mechanism does not operate. On those scales, a scalar tensor modification of gravity can alter the rate of cosmic expansion, shifting the relationship between the early and late universe Hubble constant values in ways that might reduce the tension. Some scalar tensor theories also modify the growth rate of cosmic structure, the speed at which density perturbations grow into galaxy clusters and cosmic filaments, in ways that are distinct from any dark energy model. This is important because it means modified gravity is not just a different explanation for the same observations. It makes different predictions for future observations. If the growth rate of structure deviates from general relativity's prediction in the way some scalar tensor models expect, the Vera Rubin Observatory and Euclid will see it. If it does not deviate, a significant class of modified gravity models will be ruled out. Modified gravity is, in principle, testable. The tests just require data we're still in the process of collecting. Then there are the scalar field approaches to dark energy more broadly, a landscape of theoretical possibilities that ranges from the relatively conservative to the genuinely exotic. Quintessence, as discussed, places a slowly rolling scalar field at the centre of the dark energy story. Phantom energy models go further, proposing a dark energy field whose density actually increases over time as the universe expands, the opposite of what DSI seems to be suggesting, but a possibility that certain mathematical formulations of dark energy allow, and that would, if true, lead to a future where the accelerating expansion grows without bound, eventually tearing apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms themselves in an event called the Big Rip. Models where the dark energy field couples to neutrinos, the nearly massless, nearly invisible particles that stream through the universe in numbers that dwarf every other known particle, introduce a connection between the dark energy sector and the neutrino sector that could affect both the expansion history and the neutrino mass constraints from cosmological data. Models with complicated potential energy landscapes produce dark energy fields that do not roll smoothly, but oscillate or transition between different phases, creating expansion histories with non-trivial features that could leave detectable signatures in the BAO spectrum or the CMB damping tail. The space of scalar field dark energy models is frankly enormous, and most of them share a frustrating property. They can be tuned by adjusting their free parameters to fit the current observational data reasonably well. A model that accommodates all existing data by construction is not particularly powerful as a scientific tool because it does not tell you what to look for next. The value of a theory is not just in explaining what you have already seen, it is in predicting what you have not yet looked for. The current generation of dark energy models is in many cases still in the phase of demonstrating consistency with existing data rather than making sharp, falsifiable predictions about future observations. That is not a criticism, it is an honest description of where the field is, given that the anomalies driving these models are themselves still being characterized. But it means the theoretical landscape, while rich and intellectually fertile, has not yet converged on a candidate that stands out from the crowd with the clarity that would make it a genuine successor to Lambda CDM. What unites all of these proposals, the interacting dark sectors, the modified gravity theories, the scalar field landscapes, is something more important than any individual model. They are not tweaks. They cannot be incorporated into Lambda CDM the way a new parameter can be added to a fitting formula. They require changing the structure of the theory, revising the assumptions about what the universe contains and how its contents behave, replacing simplifying assumptions that were always provisional. Dark matter and dark energy do not interact. Gravity follows general relativity at all scales. The vacuum energy is a true constant, with more complex, more dynamic, more richly structured alternatives. When you do that, you are not adjusting a number. You're proposing that the universe is built differently than the standard model assumed, that the inventory we've been working from is incomplete, or that the forces governing the items on that inventory are not the ones we wrote down. The fact that the physics community is entertaining these proposals seriously, debating them at conferences, funding research programs around them, designing future surveys explicitly to test them, is itself a signal worth reading carefully. It means the data has done something that data rarely does with such completeness and such consistency. It has driven a community of careful, conservative, evidence-driven scientists to a place where the cost of defending the old framework has become genuinely higher than the cost of replacing it. That transition from defending to replacing is not comfortable. It is disorienting, even for the people doing it. But it is, in the long view of scientific history, exactly the transition that has always preceded the moments when physics made its most important and most lasting advances. And we appear, right now, to be standing at the beginning of one of those moments. Part 18, the JWST pattern of anomalies. While the cosmological community has been grappling with the Hubble tension and the DSI dark energy signal, the James Webb Space Telescope has been generating a quieter but increasingly insistent drumbeat of other anomalies, results that do not individually break any particular theory, but collectively suggest that our picture of cosmic structure formation is missing something important. The most widely discussed of these involves massive galaxies in the early universe. Lambda CDM makes specific predictions about how quickly galaxies should form after the Big Bang. In the standard model, the first stars light up a few 100 million years after the Big Bang, and it takes a considerable amount of additional time for those stars to assemble into large, massive galaxies. galaxy formation is supposed to be a gradual process. Small halos of dark matter merge over billions of years, pulling in gas, forming stars, merging with other halos, gradually building up the large galaxies we see in the nearby universe. Massive galaxies in the early universe, within the first billion years of cosmic history, should be rare. JWST has found them in numbers and at masses that exceed what lambda CDM predicts. Not dramatically, this is not the kind of result where the standard model is off by a factor of 1,000,000. But the discrepancy is consistent enough across multiple surveys and multiple analysis teams that it has attracted serious attention. Some of these early massive galaxies appear to have assembled their stellar mass faster than our models of star formation and dark matter halo growth can easily accommodate. Some appear to have stellar populations, old, red stars, that imply substantial star formation activity at epochs even earlier than where JWST is finding them. Alongside these are the objects being called little red dots, compact, faint, reddish sources that appear in extraordinary numbers in JWST deep field images, and that, based on their spectra and colours, appear to be active galactic nuclei. Supermassive black holes actively accreting material at cosmological distances. The puzzle is the same one as for the massive galaxies. These black holes appear to be very massive, sometimes billions of solar masses, at epochs when, according to our models of black hole growth, they should not yet have had time to accumulate that much mass. Growing a billion solar mass black hole requires either a massive seed, a black hole far larger than anything present-day stellar evolution produces, or an extraordinarily efficient accretion process, or both. The little red dots suggest there may be more of these objects growing faster than the standard model predicts. None of these results has reached the level of a confirmed crisis in the way that the Hubble tension has. The galaxy mass discrepancies can be partially accommodated by adjusting assumptions about star formation efficiency and stellar mass estimates. The little red dot phenomenon might reflect unusual accretion physics or selection effects in the survey. But the direction of the anomalies is consistent. JWST is finding the early universe more structured, more evolved and more active than our models expect. And when the direction of the anomalies is consistent across independent observations, that consistency is itself a piece of evidence, not conclusive, but real. What these JWST anomalies share with the Hubble tension and the DSI dark energy signal is a common implication. The universe, at multiple epochs and across multiple observables, is not quite behaving the way our best model says it should. The anomalies are not yet pointing to a single coherent alternative theory, but they are pointing away from lambda CDM with a consistency that is increasingly difficult to attribute to coincidence. Part 19, The Temptation of Conspiracy. There is a certain kind of story that spreads quickly when institutions are uncertain. In 2023, a video began circulating online featuring a person claiming to be a former engineer involved with the James Webb Space Telescope, who asserted that the images and data being released were fabricated, that the telescope was not seeing what NASA said it was seeing, that the anomalies in the early universe were being manufactured to justify a predetermined theoretical narrative. The video got millions of views. It was translated into multiple languages. It was shared in scientific skeptic communities and mainstream social media alike. This is worth addressing directly, because the gap between genuine scientific uncertainty and motivated conspiracy thinking is one of the most important distinctions in public scientific literacy right now. The JWST data is public. Not public in the sense that a summary is available in a press release. Public in the sense that the raw data is available through the Mikulski Archive for Space Telescopes to any researcher in the world with the computing resources and the expertise to download and analyse it. The spectroscopic data confirming the redshifts of early massive galaxies has been reproduced by independent teams in the United States, Europe, Japan, and Australia using different analysis pipelines and different methodologies. The photometric catalogues showing an excess of red, compact sources at high redshift, have been confirmed by groups who had no involvement in the original discovery papers. The peer review process, for all its imperfections, is not a single point of failure. A fabricated result would have to survive independent replication by competing teams who have every professional incentive to find errors in each other's work. The reason this kind of conspiracy narrative spreads is not because people are stupid. It is because the genuine uncertainty in the science is real and visible, and uncertainty is uncomfortable. When physicists say our best model may be wrong, when Nobel laureates disagree about what the Hubble constant is, when the most sophisticated telescope ever built finds things that do not fit the theory, these are not signs of scientific failure. They are signs of scientific progress. They are the system working exactly as it should, identifying the limits of what we know and pressing against them. But to someone who expects science to be a source of authoritative, settled answers rather than a process of perpetual revision, that visible uncertainty can look like disorder. And disorder, to a certain kind of mind, looks like deception. Real uncertainty breeds fake certainty. That is one of the most reliable patterns in the sociology of knowledge. The more genuinely unsettled a question is, the more confidently false the conspiratorial answer tends to be. The universe is confusing right now, in the best possible scientific sense, confusing in the way that problems look just before they're solved. The answer to that confusion is more data, more analysis, more open debate between competing ideas. It is not a story about engineers hiding what the telescope really found. What the telescope really found is more interesting than any conspiracy. And the implications of what it found, of all of it together, the tension and the dark energy signal, and the anomalous galaxies and the fundamental questions being reopened, are strange enough that they do not need embellishment. Part 20. The Edge of a Scientific Revolution. We have travelled a long way in this story. We started with two numbers, 73 and 67, that should be the same and are not. We traced that disagreement through 15 years of increasingly precise measurements, through the elimination of systematic errors, through the confirmation by JWST that the local measurement is clean, and the confirmation by ACT that the early universe measurement is equally clean. We watched 30 theoretical proposals tested against the data and found wanting. We followed DESI as it mapped 15 million galaxies and found evidence that the force tearing the universe apart is not constant but evolving, possibly weakening, in ways that deepen the first crisis rather than resolving it. We looked at the early universe through JWST and found galaxies and black holes that appear more massive and more evolved than they should be. And we've arrived at a place where the entire theoretical framework of modern cosmology, lambda CDM, the standard model of the universe, is under pressure from multiple directions simultaneously. This is the shape of a scientific revolution in its early stages, not the triumphant moment of the new theory's arrival that has not happened yet. We do not have the replacement for lambda CDM. Nobody has walked into a conference with a new framework that explains the Hubble tension, the DESI dark energy signal, the early massive galaxies, and the little red dots, while preserving all of lambda CDM's successful predictions. That theory may be years or decades away, but the demolition of confidence in the old framework, the slow, evidence-driven erosion of certainty, is already well advanced. And historically, that is the necessary first act. Think about what happened with the ultraviolet catastrophe in the late 19th century. Classical physics predicted that a hot object should emit infinite energy at short wavelengths, an obviously absurd result called the ultraviolet catastrophe. No measurement error, no clever reinterpretation, no adjustment to the classical framework could fix it. The problem was structural. It required an entirely new concept, quantization, the idea that energy comes in discrete packets, which became the foundation of quantum mechanics. The ultraviolet catastrophe was not just a puzzle, it was a signal, a structural failure of the theory, that something in the foundations was missing. The Hubble tension may be cosmology's ultraviolet catastrophe. Or consider the perihelion of Mercury, Newtonian gravity predicted the orbit of Mercury precisely, except for a tiny discrepancy in the slow rotation of that orbit's orientation, about 43 arc-seconds per century. Small, precise, stubbornly present. Astronomers tried to explain it with an undiscovered inner planet. They proposed modifications to the inverse square law. They calculated whether atmospheric drag or the oblateness of the sun could account for it. None of the classical fixes worked. The discrepancy required Einstein's general relativity, a completely new theory of gravity, based on completely different foundational assumptions about the nature of space and time. The perihelion of Mercury was not a minor observational footnote. It was a signpost pointing toward a revolution in our understanding of reality. The Hubble tension is a signpost. The DSI dark energy signal is a signpost. The early universe anomalies in JWST data are signposts. They are pointing at something, and that something is almost certainly going to require a fundamental revision of how we think about the universe, about what dark energy is, about whether the cosmological constant is truly constant, about whether the expansion history we have reconstructed from first principles is complete, about whether there are components of the universe or interactions between its components that our current inventory simply does not include. What comes after the signposts is not known, but the history of physics is the history of following them. Every time the universe has refused to behave the way the best available theory predicted, following that refusal faithfully, not explaining it away, not adjusting a parameter to make it fit, but taking the anomaly seriously as a message about the structure of reality, has led to deeper understanding. Sometimes that understanding took decades. Sometimes it required abandoning assumptions so fundamental that the scientific community resisted for years before accepting the new picture. Always, the new picture was stranger and richer and more illuminating than the one it replaced. We are standing, right now, at one of those moments. Two measurements of the same number, both correct, irreconcilably different. A force tearing the universe apart that may not be doing so at a constant rate. A universe that formed its largest structures faster than our models say it should have. 30 proposed fixes, all ruled out. A 5 sigma contradiction at the heart of the most successful cosmological model ever built. And underneath all of it, a question that cosmology has been trying not to ask directly, but can no longer avoid. The question is not, which measurement is wrong? We know they are both right. The question is not, which of the 30 proposed fixes have we missed? We have been thorough. The question is, what are we wrong about at the level so fundamental that we have not yet realized it is an assumption at all? Because that is how the deepest revolutions in physics have always worked. Not by finding the error in the experiment, not by adding a new particle or a new field to the existing framework, but by discovering that one of the things everyone agreed was obviously true, something so basic it was never written down as an assumption because it seemed too self-evident to question, was not true after all. The universe is not behaving incorrectly. The universe never behaves incorrectly. It does exactly what it does, indifferent to our expectations and our models and our desire for a clean, consistent answer. The universe is not the problem. We don't just have the wrong answer. We may be asking the wrong question, and figuring out what the right question is, that is the work that is about to define the next era of cosmology. It may take a generation. It may take a single insight from an unexpected direction. But somewhere in the data we already have, somewhere in the contradiction between 73 and 67, somewhere in the weakening dark energy and the overgrown black holes and the galaxies that form too fast, the right question is waiting to be seen clearly. And when it is, when someone finally looks at all of this and finds the frame that makes it coherent, the universe will once again become, briefly, something we understand. And then, as it always has, it will find another way to surprise us.